So we've talked about the effect of surface roughness. Surface roughness in general increases the drag coefficient in turbulent flow. And we talked about how when you increase the amount of surface area, and you've got, right, this is especially the case for streamlined bodies, when you start increasing that surface area to make something more streamlined, more sleek, right, longer, smoother, things like that, then you're increasing the ability to have surface roughness. For blunt bodies such as circular, cylinder, or sphere, however, an increase in the surface roughness may increase or decrease the drag coefficient depending on the Reynolds numbers. So these are, when you're talking about blunt bodies, circular, cylinder, or sphere. It depends. An increase in the surface roughness may increase or decrease the drag coefficient. So it just depends. Depends on the Reynolds number. So here you can see, again, surface roughness may increase or decrease the drag coefficient of a spherical object depending on the value of the Reynolds number. And so you see you have this Reynolds number, 2 times 10 to the 5, and a smooth surface 0.5, and then the rough surface 0.1. And then you have Reynolds number 10 to the 6, smooth surface 0.1, and the rough surface 0.4. Here's the drag force relation. And then frontal area for a cylinder and sphere are here. And then roughening the surface can be used to great advantage in reducing drag. So here, golf balls are intentionally roughened. So you see those little divots, and they're not a smooth surface, right? To induce turbulence at a lower Reynolds number to take advantage of the sharp drop in the drag coefficient at the onset of turbulence in the boundary layer. This occurrence of turbulent flows at the Reynolds number reduces the drag coefficient of a golf ball by about half. For a given hit, this means a longer distance for the ball. So if you've ever looked at a ball and thought, well, why does it look like this? It's for a purpose. For table tennis, however, the speeds are much slower, much less force is put on that, and the ball is smaller, never reaches speeds in the turbulent range, and therefore the surfaces of table tennis balls are made smooth. They don't have those divots. Here we've talked a lot about drag. Now we're talking about lift. Remember, that is perpendicular, right? The component of the net force due to the viscous and pressure forces that is perpendicular to the flow direction. Perpendicular, not parallel. Okay, so you have this lift coefficient here, and then A, which is planform area, the area that would be seen by a person looking at the body from above in the direction normal to the body. For an aircraft, the wingspan is the total distance between the tips of the two wings, which includes the width of the fuselage between the wings. The average lift per unit area is here. It's called the wing loading, which is simply the ratio of the weight of the aircraft to the platform area of the wings, since lift equals the weight during flying at constant altitude. Airfoils, what are those? They are designed to generate lift while keeping the drag at a minimum. So we need to lift something up, and we need to reduce drag, or keep it as minimal as we can. Some devices, such as spoilers, inverted airfoils on racing cars, are designed for avoiding lift or generating negative lift to improve traction and control, to keep it down. You don't want a race car that is going airborne, right? It needs to stay on the ground and keep going. Lift in practice can be taken to be due entirely to the pressure distribution on the surfaces of the body, and thus the shape of the body has the primary influence on lift. Then the primary consideration in the design of the airfoils is minimizing the average pressure at the upper surface while maximizing it at the lower surface. Pressure is low at locations where the flow velocity is high, and pressure is high at locations where the flow velocity is low. Lift at moderate angles of attack is practically independent of the surface roughness, since roughness affects the wall shear and not the pressure. So here you see these stagnation points in red. Of A, an irrotational flow past a symmetrical airfoil, which is zero lift. You see those stagnation points for B, the irrotational flow past a non-symmetrical airfoil, which is still having zero lift. And then the stagnation points for C, an actual flow past a non-symmetrical airfoil, which is generating positive lift. You can see this clockwise circulation, and then the counter-clockwise circulation for the starting vortex here. Shortly after a sudden increase in angle of attack, a counterclockwise starting vortex is shed from the airfoil, while clockwise circulation appears around the actual airfoil itself, causing the lift to be generated. So this is what causes that lift. It is desirable for airfoils to generate the most lift while producing the least drag, because that makes it the most efficient, right? Therefore, a measure of performance efficiency for airfoils is the lift to drag ratio, which is equivalent to the ratio of the lift to drag coefficients. So just those. This ratio increases with the angle of attack until the airfoil stalls, and the value of the lift to drag ratio can be of the order of 100 for two-dimensional airfoil. And you can see that stall. So it's going up and up and up. We're getting, because this is the efficiency, right? So we're going up, 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 up. And then right here, we're at 100. We can't get any higher. It stalls. And then we have that reduced efficiency. One way to change the lift and drag characteristics of an airfoil is to change the angle of attack. On an airplane, the entire plane is pitched up to increase the lift, since the wings are fixed relative to the fuselage. Another approach is to change the shape of the airfoil, so we can always change those geometries to maximize the efficiency that we can obtain by the use of movable leading edge and trailing edge flaps, and you see those on planes. The flaps are used to alter the shape of the wings during takeoff and landing to maximize lift at low speeds, because remember, that's harder to get at lower speeds. It's harder to capitalize on and extrapolate. Once at a cruising altitude, the flaps are retracted and the wings return to its normal shape, kind of like a bird, with minimal drag coefficient and adequate lift coefficient to maximize fuel consumption while cruising and at constant altitude. And so that's why you'll see those go down. Note that even a small lift coefficient can generate a large lift force during normal operation because of the large cruising velocities of an aircraft and their proportionality of lift to the square of low velocity. And so you can see these changing here. The flaps extended for landing, and then the flaps retracted for cruising. So here is the effects plotted on the lift and drag coefficients of an airfoil. And the minimum flight to velocity can be determined by the requirement that the total weight of W of the aircraft can be equal to the lift and CL and the CL max, respectively. For any given weight, the landing or takeoff speed must be minimized by maximizing the product of life coefficient of the wing area. One way we do this is to use those flaps that we just talked about, extending those flaps out. Another way is to control the boundary layer, which can be accomplished simply by leaving flow sections, slots, between the flaps. Slots are used to prevent the separation of the boundary layer from the upper surface of the wings and the flaps, and this is done by allowing air to move from the higher pressure region under the wing to the lower pressure region on the top surface. So it can go, you see it goes under and over. right? You have that slot. So here's a variation of lift coefficient with the angle of attack for a symmetrical and non-symmetrical airfoil, respectively. So it increases almost linearly with the angle of attack, reaches maximum, and then starts to decrease sharply. And that decrease of lift with further increase of the angle of attack is called a stall. And it's caused by flow separation when it just stalls out. That's kind of easy to picture, right? When you have that flow separation and the formation of a wide wake region over the top surfaces of the airfoil. Stall is highly undesirable since it also increases drag at zero angle of attack. So that's equal to 0 degrees. The lift coefficient is 0 for symmetrical airfoils, but non-zero for non-symmetrical ones with greater curvature of the top surface. Therefore, planes with symmetrical wing sections must fly with their wings at higher angles of attack in order to produce the same lift. And here the drag coefficient increases with the angle of attack, often exponentially. We just kind of talked about that. Therefore, large angles of attack should be used sparingly for short periods of time for fuel efficiency when you're just really wanting to capitalize and extrapolate any efficiency that you can get. So finite spanned wings and induced drag. So for airplane wings and other airfoils of finite span, the end effects at the tips become important because of fluid leakage between the lower and upper surfaces. Okay? Pressure difference between the lower and surface, so high pressure region, and the upper surface, low pressure regions, drive the fluid at the tips upward while the fluid is swept back because of the relative motion between the fluid and the wing cutting through. This results in that swirling motion that we saw. Remember, we had something, kind of swirling this way and then swirling that way. Swirls in a swirling motion that spirals along the flow called the tip vortex at the tips of both wings. Vortices are also formed along the airfoil between the tips of the wings. These distributed vortices collect towards the edges after being shed from the trailing edges of the wings and combined with the tip vortices to form two streaks of powerful trailing vortices along the tips of the wings. So you can see these here. They're just trailing. See trails here. This one you've seen a lot, right? I would think, see, crop duster flies through smoky air, which swirls around in one of the tip vortices from the aircraft's wings. And then here, it's been determined that the birds in a typical flock can fly to their destination in a V formation with 1/3 less energy by utilizing the updraft generated from the bird in front. And that's why this bird always changes out, because this guy cutting through the air is doing the most work. The bird at front is always doing the most work. That's because he's producing these drafts that's helping to alleviate some of the work in the birds, and so he will eventually go down to the back and one will come up. Military jets also occasionally fly in a V formation for this exact same reason. We really depend on birds for our flight. A, geese flying in their characteristic V formation to save energy, and then B, military jets imitating that as well. So we do have an aspect ratio. That is the ratio of the square of the average span of an airfoil to the planform area. For an airfoil which a rectangular planform of the chord C and span B, aspect ratio is a measure of how narrow an airfoil is in the flow direction. So this is what it is. It is a measure of how narrow an airfoil is in the flow direction. So here, bodies with large aspect ratios fly more efficiently, but they are much less maneuverable because of their large moment of inertia. So here you can see a a bald eagle with his wing feathers fanned out during flight. And then winglets are used on the sailplane to reduce induced drag. So we can get lift generated by spinning, and you still have, here's A, potential flow over a stationary cylinder. You still have those stagnation points. And then B is the potential flow over the same cylinder, just in rotation, and you're experiencing some of this lift. And you still have those same stagnation points, but you have this low velocity, high pressure, and then coming over here, you have, it kind of spins around and you get that high velocity, but then that drop in low pressure. The Magnus effect is the phenomena of producing lift by the rotation of a solid body. When the ball is not spinning, the lift is zero because the top and bottom symmetry, you don't have any change in that low velocity, low pressure, high pressure. But when the cylinder is rotated about its axis, the cylinder drags some of its fluid around because of the no-slip condition, that stickiness, right? And the flow field reflects the superposition of the spinning by non-spinning flows. Just a little note, this is the idealized potential flow. So here, this is the lift coefficient strongly depends on the rate of rotation, right? And also roughness affects the drag and lift coefficients, and therefore golf balls, we talked about this, with the right amount of roughness travel higher and further than smooth balls for the same hit, and that's directly related to the Reynolds number. So we couldn't enter into this drag and lift chapter without talking about the Wright brothers. They are truly the most impressive engineering team of all time. Also the most brave. Me being an engineer, I don't know that I would I don't think that I would get on that, right? No, definitely not. So not only impressive just in what they were able to accomplish, but impressive in their bravery. Self-taught, they were well informed of the contemporary theory and practice in aeronautics. They both corresponded with other leaders in the field and published in technical journals. While they cannot be credited with developing the concepts of lift and drag, they used them to achieve the first powered, manned, heavier-than-air controlled flight. They succeeded while so many before them had failed, because they evaluated the designed parts separately before the Wright brothers' experiment were building and testing whole airplanes. So here, and also someone before them that is very popular for doing just different kind of flight equipment is Leonardo da Vinci. So flying in nature, lots of them. Birds, insects, and other flying animals generate lift and thrust in manner and produce high agility and also efficiency. Leonardo da Vinci studied the flight of birds and designed a flapping wing device a long time ago. This topic is still fresh and still complicated. Classic aerodynamic theory is appropriate only for fixed-wing aircraft or gliding animals, where lift is obtained primarily by attached flow over a nominally rigid wing, and fails to predict the generated lift of insect wings. And I will tell you, the wings of insect, they say that while we do study birds, and especially insects, the flight and lift and wing that they are able to put all together is truly astounding. The most aerodynamic animal, and we're talking about aerodynamic in the foundational realm, in that it can be any, object cutting through a fluid, whether that be liquid or gas, that the most aerodynamic animal on the planet is actually a shark, which I think was great to hear. I definitely thought it would be something given that it's much easier to cut through air than it is water. But yeah, a shark is actually the most aerodynamic animal on the planet. The paradox that bumblebees can fly, despite the aerodynamic theory, suggests that they cannot generate enough lift. Clearly they can. Has been largely resolved through the discovery of unsteady mechanisms of lift generation and the dominant leading edge vortex formed on their flapping wings. So this is really, I love the paradox that bumblebees can fly, because if you look back, there's tons of paradoxes, right? There's tons out there, and there's tons of things that we discover and that we move towards, and then not everything in nature behaves according to that. And it's funny because they say, oh, well, it's a paradox, and oh, but this is, what it is. But really what you tend to see is that we just haven't figured it out enough, right? It's because we have to discover something else. There's something else that we need to investigate, to find. And then that opens up unsteady mechanisms of lift generation and the dominant leading edge vortex formed on their flapping wings, it's amazing, right? And so that's something else that we can implement into our man-made machines, because clearly bumblebees have perfected flight. So here, Ellington, 1996, were the first researchers to visualize a tornado-like vortex that ran outward along the leading edge of each wing by releasing smoke around the wings of a hawk moth. And similar, Bomfrey in 2006 showed the complete vortex loop induced by the moth highlighting the main wake elements. And then these LEV, leading edge vortex structures on top of the wing, generate lift beyond the values predicted by traditional aerodynamics. And this is amazing to see, right? But these are very new. This is new, right? 1996, 2006, this is relatively new, considering that lift and drag are natural phenomena. So they've been in existence as long as existence has happened, and there was a solid body that could cut through some kind of fluid. Researchers have studied the aerodynamics of birds and insects to quantify the extra lift and build robots that can fly like real animals. Festo Company has designed and built an ultralight but powerful flight model, which can start, fly, and land autonomously with no additional drive mechanism. So that's amazing. So just based on the material, the geometries, the ability for things to bend, maybe this beak can point down, things like that. So it doesn't need anything else to drive. It doesn't need anything to apply that force. Gliders, when the birds stop flapping and keep their wings stretched out, they can generate only lift, and that regime is known as gliding. Gliding animals tilt its direction of motion slightly downward relative to the air, and thus the gliding angle directly controls the lift-to-drag ratio. The exception is hummingbirds. All flying birds can glide to some extent. As a rule, the smaller the bird, the shorter the distance it can glide, and the faster it sinks. And that's because it's definitely dependent on the surface area, right? Large birds, to generate thrust and lift for forward flight, large birds like pelican, geese make use of vertical plunging motion in combination with rotational motion of wing during a downstroke, or this downward wing motion. In contrast, the upstroke, which is the upward wing motion, is relatively passive, and the wing is rotated to a near zero effect angle of attack. The wing size and flight velocity are large enough for flight in this regime. Flapping frequencies are quite low. It takes a lot of energy to flap, right? The amplitude tends to be high, and the flow field is effectively attached throughout the flapping motion. Medium birds, pigeons, use a combination of plunging, pitching, and rotating motion to generate lift and thrust forward, and hovering flight. So it uses what it has in a combination to get it to lift, and it's done by practice, right? Small birds and insects, when the wing size decreases to such small scales, like insects and hummingbirds, the flight speed also decreases, right? And to some extent, it leads to an increase in flapping frequency. So we know that hummingbirds flap so fast, it's difficult to see, right? And while hummingbirds are extremely fast flyers, they are not flapping across an ocean like a plane, right? And then we've talked a little bit about it. How do birds, insects use flapping wing motion to fly? And so here you can see that. You can see the structures form, the vorticity. You can see these forming off of these alternating patterns, A and B. Vorticity is the local rotation of the fluid, and it's created on the surface of the wing. It separates the high angles of attack and rolls itself up into discrete vortices. Many birds and insects create large trailing edge vortices with their wings when they move through the air. Can we expect to see large airplanes with flapping wings in the near future? Flapping flight is fascinating but very complicated. I could also expect it to be very turbulent for the passengers, right? So if you think of a bird that is flapping its wing, unless it's flapping exponentially fast like a hummingbird, the body of the animal is moving. So then that would mean if it was a plane, then everyone inside that body would be moving. However, what I think is maybe more attainable in the near future is a personal flight device like what Leonardo da Vinci imagined. So something that is just moving one or a couple of people. And I think that would be awesome to see. So here's some of the summary that we went over. And right now we'll move to a short video that'll just help put some of these in a more moving picture.
Leonardo da Vinci's flying machines. Leonardo da Vinci's inventions covered a wide variety of fields, but the area in which he was arguably the most inspired was aviation. Although he was often constrained by the technological limitations of the 15th century, and his designs were sometimes flawed, da Vinci's flying machines showed a scientific, creative, and forward-thinking mind that was far in advance of many of his contemporaries. The ornithopter. One of the most well-known of all da Vinci's inventions was his ornithopter. Unlike the fixed-wing aircraft with which we are all familiar, the wings of an ornithopter flap up and down much like those of a flying animal. Da Vinci was not the first person to think of this form of flight. In fact, the earliest description of an ornithopter can be found in the Ramayana, which was written sometime between the 5th and 1st centuries BC. There were several attempted flights made well before da Vinci's time, although it seems unlikely that the highest achievement of these was a sustained glide rather than true flight. When looking for inspiration for his own device, da Vinci drew heavily from nature, basing the design on the flight of bats and birds. He is famously quoted as having said, "Human subtlety will never devise an invention more beautiful, more simple, or more direct than does nature, because in her inventions, nothing is lacking, and nothing is superfluous." In da Vinci's ornithopter, the pilot would have been placed lying face down on a wooden board at the center of the device. The frame would have been made out of pine and raw silk, and the wings, which were to have been pointed like those of a bat and spanned 33 feet, would have been powered by a pedal crank and a rod and pulley system. The ability to steer was to be provided in the form of a headpiece, and a hand crank would be available in case the pilot needed a way to generate further power. Although there's no evidence that the device was ever built, let alone tested, during da Vinci's lifetime, it seems likely that he would have been aware of its single serious flaw. Although a sustained flight may be possible once in the air, no single human could possibly have the strength to generate the power necessary for takeoff. The helical air screw. Although the Chinese deserve the credit for first working out the concept of rotary flight, it's Leonardo da Vinci's helical air screw that is usually considered the first attempt at designing a fully operational helicopter. Although the basic principle remains the same, da Vinci's air screw bears little resemblance to what we would recognize as a helicopter today. The machine consisted of a circular central platform upon which its pilots would stand, a long shaft and a large screw-shaped canopy made of starched linen. The pilots would power the device by twisting cranks, which would, in turn, rotate the shaft and, in theory, create lift. Although da Vinci's design was undoubtedly well ahead of its time and demonstrated a clear understanding of the physics that underpin how modern helicopters are able to gain elevation, the technology of the late 15th century had simply not evolved to the point where a fully functional machine could actually be constructed. Although there was no attempt to build one during da Vinci's life, modern reconstructions have shown that the machine was simply too heavy to ever take off. The parachute. Perhaps the most successful of all da Vinci's aviation-related inventions is his parachute. Da Vinci firmly believed that if a person used a large enough piece of linen, then they could safely jump from any height without risking serious injury upon landing. The end result of his pondering was a hastily drawn sketch in the margin of one of his many notebooks, depicting a person dangling from the center of a pyramid-shaped canopy. The linen was to be supported by a wooden frame made up of a 12 by 12 yard square at the base, with 4 poles rising to a central point. As with his other flying machines, da Vinci's parachute remained entirely conceptual throughout its lifetime.